and just formally start. So, okay,
Yes.
so Davide Gaiotto will continue his mini course on categorical Hooft expansion.
Okay, so let me remind you that, the general picture that we presented in the previous slide, previous lecture. So we have a gauge theory with a UN gauge group or something like that. We study its formal deformations in perturbation theory, perhaps after adding a collection of fundamental modifications, and I'm going to discuss more precisely what that means. And there is this Hooft expansion, which reorganizes the perturbable expansion by sort of attaching a factor of h bar to every factor of n, essentially. After you do that, formally, what you have has the same structure of sort of a quantum string theory, a quantum string theory involving open and closed strings. Then you can send h bar to 0 while keeping an nh bar fixed. And this gives you a classical string theory with open and closed strings. And now there is another sort of formal identification. The data of this classical open and closed string theory is just an infinity category with some properties, Calabi-Yau category. So it's the same sort of data which emerges when you study formal deformations of a 2D topological field theory with boundaries. And furthermore, by the cobordism hypothesis, this data just defines the two-dimensional worldsheet theory with boundaries. And then the claim is that if you use this, if you do the genus expansion of this topological field theory in the sort of classical, typical, the traditional string theory sense, this should reproduce the full Hooft expansion of the quantum field theory. So, starting from every UN gauge theory, you can, in principle, all of the steps are, rigorously, either rigorous or close to being mathematically rigorous. So, ultimately, you might hope to get a theorem or at least a rigorous conjecture, where for every gauge theory, you compute the 2D TFT data, and then you try to reproduce the Hooft expansion as a genus expansion. I started describing the matrix model as an example of this picture. So let's go to the matrix model here. So a matrix model is just a matrix integral. It's an integral over a space of matrices with an action which is UN invariant, where UN acts by conjugation. Maybe there are simple variants of this idea where you have bigger gauge groups. A very general class of matrix models is labeled by a quiver with potential. Essentially, you have every node of the quiver is a gauge group, every arrow of the quiver is a matrix, and the potential is literally the action of the matrix model. So the potential is the sum of traces of cyclic words made out of the fields. You can look at this matrix model in various ways. Traditionally, people write down the integration by part identities for the matrix model and call loop equations, and try to study this function using,
David, may I kind of to be slightly more pedantic? So if you have a quiver with a potential, then you have this three Calabi-Yau category, you have various complexes like cyclic, whatever. Good. But you do not have any choice of integration cycle, and you do not have a measure from this data.
So as for the measure, I'm just going to take, just the product of all elements of the matrices.
Yeah, but it's something which you kind of, it's not very invariant.
Absolutely, but in the BV formalism, redefinitions of the variables. See, I was mentioning integration by part identities. Integration by part identities is essentially the response to a change of coordinates. So all of those ambiguities will be automatically dealt by the BV formalism. That's not a concern.
But your form, I mean, at least as it's in this slide, it's a restriction of some Calabi-Yau form on the complex, whatever.
Yes, absolutely. It's the Calabi-Yau form on mat n to the power little n.
Okay, okay. And the cycle
The
you
cycle
said
is very
last
important.
time, yeah, but you said that somehow you can choose an appropriate one, but it's
So,
theory dependent or what?
well, so the equations the equations satisfied by this integral, the integration by part identities, are independent of the cycle.
Mm-hmm.
When you do a perturbative expansion, you'll pick a critical point of W. Typically, it will work if W has, non-degenerate Hessian. And then you do perturbation theory. When you do perturbation theory, you're automatically integrating over the Timbo for the critical point.
Well, it's for the Morse, yeah, but sometimes it's not more. Okay, but
Absolutely.
ideally you have, yeah,
But
yeah.
the point is that I'm going to derive differential equations satisfied by this integral, which
Mm-hmm.
are true for every gamma. And they will be satisfied automatically by any perturbative expansion that makes sense.
Mm-hmm. Mm-hmm. Yeah,
So I will
okay.
not really think about the perturbative expansion of the partition function itself as much as the equations it satisfies.
But let me ask you another question.
Mhm.
If you work just with perturbative expansions, like assume just hypothetically that all critical points are Morse, and
Mhm.
so you have just a bunch of formal series, yeah, in
Yes.
H bar,
Yes.
which also depend on the structures, kind of mathematical or whatever, formal structure which we are looking at, do they depend only on this collection of formal series, or there is something else, interaction between these formal series? Because when you have you see
Yes.
this idea that you have only perturbative
Mhm.
expansions and you have kind of interaction between these
Yes. So the
symbols,
whole
whatever.
adjuvants is
Yeah,
definitely
yeah, and then you have the subject of
yes.
research, but the structures you are talking about, are they purely formal or they depend
So in
on
this seminar, I
some
will only talk about essentially the differential equation satisfied by this exponential integral.
exponential integral, or it's enough to look for formal expansion and
I will not
apply?
even try to expand it. Indeed, my favorite potential is going to be
All right.
trace of x commutated of y and z, which doesn't have isolated critical points.
Yeah, but still there are some mathematical formal structures. You know this cohomology with a sheaf of vanishing
Yep.
cycles, and so you
Yes,
can
but
look.
exactly. So I will study the BV complex, right? The BV complex, the cohomology of the BV complex is literally the cohomology of integration cycles, right? Of integrands, really.
Yeah, okay.
So that is literally what I want to study, the BV complex for
Okay.
this. So indeed, I work in the BV formalism. There is you can write a you take your trace of W, you add a bit of contribution from the ghosts, which is useful to make sure that you're talking about the gauge theory. I call this SW. I will not write it explicitly, but it's essentially the action for the cyclic 3D Calabi-Yau algebra attached to the quiver by Kontsevich and Solomon. And you can take this action, this BV action, you can deform it by in the most general way, right? So you can add linear combinations of all possible traces built out of fields, anti-fields, and anti-ghosts. So you have a collection of couplings tau, which just pretty much by definition is an element in the cyclic homology complex of this algebra, AQW minus the augmentation ideal in this algebra. Because I don't want to use the ghosts. It's a long there is a story there, but it doesn't matter. So it's just take its definition. I'm doing this. I take the cyclic homology complex valued in the augmentation ideal. I use these traces to deform. I look at it as the space of formal deformations of my BV action.
So how should I think about the product of tau, which is element of the cyclic complex, and trace of W alpha? It's so your SBV again pedantically it
Yes.
belongs to what
So,
set?
the traces are a basis for the cyclic cohomology complex. The tau are just numbers that I put in front, formal numbers I put in front of these traces. And so the collection of
what's
tau.
I'm confused. What's the relation between tau alpha and tau?
Tau is the collection of tau alphas.
So you choose some basis and
Yes.
in cyclic homology. Okay.
That's right. So tau alpha, if you want to be concrete, a trace of x, 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 y, z. But otherwise, tau, the space of BV actions is the cyclic homology complex. So this algebra A, so you can package all the fields, anti-fields, ghosts, and anti-ghosts as a single field valued in A.
Yeah, or in terms maybe mathematically, if I start with literally potential as a cyclically invariant function element of the path algebra of the quiver, then I can extend it to kind of a DG object. Probably that's what you're
Yes,
doing.
yes. So I'm not just using the arrows of the quiver. I'm using the arrows and the anti-arrows and the anti-loops.
Yes, with degrees. Yes.
With degrees, absolutely. So this right.
Okay.
Okay, that's right. So the taus that have sort of those numbers 0 are the original coefficient. They're sort of literally the formal deformations of W. And then there is some hair in Heidegger's number, which helps me define the whole BV complex and help me formulate the integration by part identities in the right way.
When you say Kontsevich Soibelman cyclic whatever 3D, what do you mean?
I'm desperately trying to find a name for the algebra whose Koszul dual is the Ginzburg algebra.
Okay. Koszul, when you say Koszul dual, you mean
The bar complex of Koszul dual. So the Koszul dual in the sense of infinity.
Because let's because there are maybe some algebras here. I don't know.
Yes.
So if you take quiver with a potential, there is this Jacobi algebra, quotient of the path algebra by cyclic derivatives. It's associative. Okay, good. Then you can take Ginzburg algebra, which is DG algebra quasi-isomorphic to this Jacobi. And gamma QW, it is Ginzburg algebra.
That's right. It's the right critical locus.
And what should I do with this DG algebra in order to get Koszul dual?
No, I want to start from A. I want to say Koszul dual is gamma. But
No, but I don't know. Maybe not everyone understand what do you mean by Koszul duality, because for quadratic algebra, you see, some people know.
No, I only do infinity stuff. I'm a physicist. So
yeah, when infinity, you should explain what does it mean. You take
so a shriek is what is it? The essentially it's just the tensor algebra of A divided by the augmentation ideal of A. Equipped with as an algebra, the tensor algebra, and then you put a differential which essentially is dual to the matrix to the composition of the algebra, which I'm not going to try to describe.
Okay.
Right, it has the property that
yeah. Now I understand what do you call it.
Moret-Cartan elements in A. Yeah, what is it? Sorry. A modules are Moret-Cartan elements for A shake.
Yeah,
right?
Yeah. That's probably some
or the other way around.
Interpretation of the cyclic complex in terms of differential forms.
Yeah, I get there to the next page, so we get there.
Yeah. Okay.
Yes. But for now, right, I'm just saying, just by looking at matrix model, I see emerging the cyclic complex. The differential comes about when you try to do, sorry, I need to erase the annotations. Okay. The differential comes about when you Sorry. Yes, when you look at the quantum master equation. So you can ask, normally people impose the quantum master equation as an equation. They say, okay, I have my action, BV action, I want delta BV, the BV Laplacian, to kill e to the s. I prefer to impose the quantum master equation in a derived way. So I'm gonna write down the differential operator that acts on the couplings, this Q, such that Q plus delta VV annihilates the action. How does this Q look like? If you process this equation enough, you see that Q is essentially a second order differential operator. It has three terms. One, this tau bracket tau contracted with the derivative, the one in the middle. This is literally the first term. Let's do the first term first. The first term is a fine linear in NH bar. D0 is literally the differential in the cyclic homology. So if you just look at D0 acting on the couplings, you get your cyclic homology complex. D and H bar is a deformation of D0. I'll describe it momentarily. Well, I can describe it immediately. So essentially, the cyclic homology complex differential can be understood as a BV bracket between a generic trace and the action, the original BV action. This deformation instead uses the BV Laplacian to contract two consecutive symbols in a trace. When you do that, you get an extra factor of n, and that's why you get this, something proportional to NH bar.
Yeah, but sorry, when you assume that you can solve this derived quantum master equation.
Oh, I'm not solving it. That's the whole point.
No. But suppose you have this SBV. Is it true that the equation has a form like the bracket with SBV plus this Laplacian? Is it applied to something is equal to zero? Like
absolutely. I mean, so the delta BV. Yes, I mean, I wrote it in an exponential form. If you want to, you can write it.
You
can expand it out.
Yeah.
But in practice, you literally have e to the s, and you're acting with the BV Laplacian. The BV Laplacian takes two symbols and removes them. Right, and so if remember that I was looking at, SBV was SW plus deformations. SW satisfies the quantum master equations by itself, and I'm looking for deformations. And one of the pieces of the answer is the BV bracket between SW and the traces, which is this thing here. And this gives you D0 tau, del tau, because it takes a trace and spits out a trace. So it takes a tau and then gives you a derivative with respect of tau that pulls down a trace. Then there is something which again acts on a trace, but on two symbols within the same trace. If they are consecutive, you get a single trace back with a factor of n. This correction to the differential. Then there is another thing, piece that is the BV bracket of two traces. This takes two traces and spits out one trace. So this is T bracket T, the T. This bracket is the usual bracket on cyclic homology that you might already know. It's a well-known operation on cyclic homology. And finally, the BV Laplacian can contract two symbols and the trace which are not consecutive. Now, I wasn't writing Riemann graphs here, but if I had, you would see that the result is actually the product of two traces. So this operation takes one tau and produces two derivatives with of tau that pull down the traces. So this is the second order differential operator on the couplings. This dual bracket is literally a dual bracket on the cyclic homology. The bracket and the dual bracket together make it into a dg-Libby algebra by algebra. So just by studying this equation, we found a dg-B algebra structure on the cyclic homology of the augmentation ideal. Any questions?
So your tau, it's deformation parameters of the potential, if you
Yeah,
like,
and it's an
whatever.
element of the cyclic homology.
So then when tau is goes to 0, what survives? I would like to see how it, yeah.
If tau equal to 0, you get 0. I mean, everything is linear, has at least one tau.
I don't know. Yeah. It's a product. So Q, yeah. Yes. All right. All right. Yeah. Okay. Mm-hmm.
So the main property of this Q, if you were to study the matrix integral, is that Q annihilates the partition function. Notice when you do an integral, of course, when you do an integral, you set to 0 all the antifields, and then you integrate over the fields, right? So a lot of these taus drop out. You just get a function of the tau equals number 0. When you say the Q annihilates that, right, it means that the part that is linear in the tau equals number 1 vanishes. So you get a whole bunch of differential equations that annihilate the partition function. The rest of Q is sort of giving you the derived structure. Right? You had a bunch of equations, but these equations had redundancies, and their equation satisfies by the equations, and so on and so forth. This Q sort of packages everything together, gives you the full formal deformation space of the problem as a BV infinity manifold. Sorry, BV infinity structure, right? So you have a manifold, a formal pointed DG manifold with an important differential operator equals number 1, which is not a linear, it's not a vector field, but it's a second order differential operator in this case. Okay. Now I want to take the classical. So this data here is the analog of this quantum master equation of the open closed string theory. I could push the analogy a bit farther. I just worried it would be more confusing than useful. But if you look at the first piece of Q, you should recognize it's sort of a Chevalier-Ellenberg differential for the cyclic cohomology, right? So physically, the Chevalier-Ellenberg complex is what you use to study gauge theory in one dimension. So if you want to have some holographic interpretation, you have this zero-dimensional matrix integral, and you're trying to describe a one-dimensional dual to it. It's a quantum mechanical system. There is some kind of a BRST charge, this Q, and there is a state, which is the partition function, which is annihilated by Q, so it's gauge invariant. But anyway, these words don't need to mean anything. I'm not going to mention them again. You can just ignore them. Let's do the classical limit of this quantum system, which means I'm going to convert the derivative, h bar squared the tau. It's like a conjugate momentum for tau. I call it pi. So now I have a phase space, a formal pointed phase space, with coordinates tau and pi. So it's got a cotangent bundle of the shifted cyclic homology complex. And on this phase space, we have an Hamiltonian, an odd Hamiltonian Q, which has this nice form. There is a tau pi, a tau tau pi, and a tau pi pi. So you get a derived phase space, or you could also call it a cyclical infinity algebra. So our conclusion is that we found a cyclical infinity algebra structure on the cotangent bundle to the cyclic homology. And now I would like to figure out, what does that mean? Because as Jan was mentioning maybe some time ago, this sort of algebra, this 3D Calabi-Yau algebra A of QW defines a 3D Calabi-Yau cone, denoted as Y QW, or some non-commutative version of that. And when this is geometric, when it's not, when it's commutative, the cyclic homology has a very well-known interpretation. It computes a piece of the polyvector field complex for the Calabi-Yau cone. So one vectors and bivectors, essentially.
So since you mentioned me, you mean that this Jacobi algebra that defines what you call 3D Calabi-Yau cone, or what? AQ. So
yes, exactly. So it defines a Calabi-Yau cone.
Okay.
When
Yeah, for
Maybe say
example,
differently.
for X commutator with YZ, for this potential, it will be simply C cube.
That's right. That's right. So the toy model I would like to focus on is C cube as the quiver with one node and trace
Three
of
loops and
XYZ
cubic, yeah. Yeah.
potential.
All right. So then the Cazul dual will be the Grassmann, I mean this
Yeah, that's right. In
exterior
that
algebra
case,
of
in that
thing.
example, A is so gamma is isomorphic to C of Z1, Z2, Z3, and A is isomorphic to C of three odd variables. I cannot write thetas here. Do you see these annotations? Like the notations?
Yeah, that's fine. And so then your phase space will be the cyclic complex for this
The cotangent to the phase of the
cotangent
cycle.
plus tangent. So it's sort of altogether, it's kind of cotangent space to one half of it. It's probably because this sum it should carry some word symplectic structure for which both amounts are.
No. It's a standard symplectic manifold
Yeah, yeah.
with with a non-Hamiltonian.
All right. Yeah. Okay. Good.
And I want to compare it with PV1 plus PV2 plus the dual. So the
Can I see it in this toy model example?
yes. Next slide.
All right.
So right. So my question is, what's the meaning of this phase space geometrically? So drawing. Okay. So I want to give a meaning to this in terms of removing the tip of the cone. So let me study the manifold C3 minus the origin. Technically, I want to study the B model on C3 minus the origin, which is the AKSZ sigma model on the shifted cotangent bundle. Anyway, so in this context, it's natural to study divergence-free polyvector fields on C3 minus the origin. Or if you prefer, you can convert the polyvector fields to del closed forms in C3 minus the origin. Now, my observation is that this space does have a nice symplectic pairing. It comes from integrate this expression, integrate over S5, form times del inverse of the other form. So this gives you a symplectic pairing essentially between P0 forms and 4 minus P2 forms. This is almost a symplectic pairing because it misses one single thing. It misses the the Beltrami-Martinelli kernel, which is a 0-2 form whose del bar is the delta function of the origin. This form under this pairing would like to pair up with the del of 1, but del of 1 is 0. So it's an almost symplectic form. It means, it's a kernel, has a kernel which is one-dimensional. And so you can make a claim that polyvector fields in C3 minus the origin are the cotangent bounded polyvector fields in C3 plus this single extra line. And now, but if polyvector fields are an L-infinite algebra, they are Lie algebra, and there is symplectic form, so I do get a cyclic L-infinity algebra. And I would like to conjecture that there is a quasi-isomorphism. If you take the space parameterized by taus, pi's, and nh bar, this should be quasi-isomorphic to the polyvector fields in C3 minus the origin.
So this is your formality theorem.
Yes, conjecture.
Well, yeah, conjectural formality conjecture. Actually,
Yes.
for Kontsevich, it also first was a conjecture, then it became. Yeah, and so hold on. The first two things, pi and tau, it's a sort of a cotangent space
To the cyclic homology.
to this whatever homology or to complex if you work in
Right, to the
infinity.
cyclic complex, right? To the
Yeah,
cyclic
yeah.
complex
And
of H.
NH bar, it's why you included?
I include an H bar because if you go look at Q, there was this term, and see, this term, I write it as D and H bar N, but it's really a D0 plus NH bar times something. So I'm saying, I want to include this NH bar among the pies, if you want, uh, as an extra pi. I mean, it's an extra variable. Like I'm treating this NH bar as an extra variable which doesn't have a conjugate momentum.
Yes, so which means that it converts your symplectic graded vector space to something which is rather
Yeah, it's Poisson with symplectic leaves.
contact or whatever contact maybe because
Maybe
you add
complex
an
better prepared, yes.
additional NH bar. It's your lambda was lambda or something you
Yes,
denote.
yes.
Yeah,
Well, if I were to be super precise, if I have a quiver with multiple nodes, I can have multiple ends because each node can have its own rank. So there could be
yeah.
multiple NH bars.
Ah,
So that's why I
then you
think it's
have
a
linear
complex.
combin. You have some for different. Okay.
Yes, so I get a family of Qs with multiple parameters.
Complicated. Yeah. Okay.
And literally, you should think about taking C3 minus the origin. This can be deformed by this polyvector field, omega Beltrami Martinelli. It's a weird deformation because it's not geometric. I mean, but it's part of the deformation complex of C3 minus the origin.
So then, if somebody is not interested in quantization, like there is deformation quantization for which you have a formality theorem between polyvector fields and some whatever complex of polydifferential forms. So if you are interested just in polyvector fields, so you say that there is a symplectic structure which for which so you have sort of a odd symplectic graded symplectic manifold with additional no you don't need anything. It's odd symplectic, so then you can look for graded functions such that the bracket with itself is equal to 0. That's your classical BD. All right.
Yeah, so here for every Q and W, which have a geometric, you get a conjecture, and conjecture in this complex, meaning this derived space, is quasi-isomorphic to polyvector fields on the cone minus the origin.
Yeah, the right-hand side is more or less clear because it's some classical spaces.
Yeah.
When you say div means what?
Divergence free.
Divergence free. Good. But when you say left,
The left is completely explicit because it's just the space of tau and pi's inside the cyclic homology complex.
So, for example, if I start with this toy model like A to be a Jacobi algebra for a quiver with a cubic potential,
Yes.
all right? So then my classical object is just C cube, and I literally do what you wrote, remove the origin, blah, 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 and get it, okay. And on the left-hand side, I should do something. I should consider Kazul dual to Ginzburg, so I should write down the Ginzburg algebra, then take...
No, I prefer you just work with A. You take the cyclic complex of A plus its dual, and you just do these calculations, which I have denoted graphically here, but they're completely explicit. You just and this is not. I mean, there is a math paper I can give you the reference which defines this by algebra. So you don't even need to.
Who did it?
Well, I can try to find perhaps not in real time. But
Maybe not immediately, but
so it's known that this cyclic complex is a bialgebra.
I believe in that. I simply but what I mean that in formality theorem, like with Kontsevich, that's a kind of a model. And actually, there is a cyclic formality theorem for cyclic chains. I believe
Yes.
Shoy had proved it for the first time, or at least formulated. But there is a parameter which is h bar, which kind of distinguish between classical and quantum. And in your case, it's what? Is NH bar or it's something else?
No, so
Or it's tau, because I'm kind of
I don't
confused.
know which h-bar you're talking about in the cyclic theorem. So there is a theorem that cyclic homology of A is isomorphic to polyvector fields, right, on the cone.
Yeah, yes.
Yes. So I'm giving an upgrade of the theorem for the cone minus the origin. And I use cyclic homology as a bialgebra instead of as the algebra.
Cone minus origin and you need cone minus origin in order to you need to remove origin in order to have a symplectic structure.
Yes, that's right.
Otherwise, you don't have it.
Yeah, that's right. I should have said it more explicitly. This pairing pairs up polynomials with derivatives of the Beltrami-Martinelli kernel. So with removing the origin adds a bunch of 0, 2 of p, 2 objects, which are dual to the original ones. Most of them except one. This is
okay. All right.
Okay, so this by itself is already a conjecture. Would be nice to prove for generic Calabi-Yau cone, 3D Calabi-Yau cone. And I understand there is a way to define the cone minus the origin even for non-commutative cones by looking at the category of coherent sheaves and removing one object or something like that.
Yeah, I think it's a purely formal thing which you can do on the A side and on the B side. You have, and the model is indeed, that's probably will be understandable for everyone. You have, I don't know, maybe Calabi-Yau manifold, say non-compact, maybe, and you have a closed subset, and you can consider indeed derived category of coherent sheaves on the big things supported on this compact or maybe on closed subset. So this is something like supported at the origin, if you'd like. If you want to remove, you localize.
Right.
And which means that you take the quotient of the big category by the category of those supported at the origin. So that's and indeed it seems to be non-compact but smooth. Yeah.
And so it would be nice to prove that this is quasi-isomorphic with this explicit.
No. I'm just translating dictionary. Yeah. No.
I'm saying using the translation, one can make a conjecture of all QW.
Yeah. Okay.
So that would be nice to prove. Okay, now I want to say something about the quantum version. Trying to recover the whole differential operator instead of the Hamiltonian. So there's an idea which I'm borrowing from Keiju Zheng, sorry, I'm very bad at pronunciation, which is to start with the BCOV theory, which is the B model on C3, say, minus the origin, and to do a Closed-Klein reduction on S5. So the idea is you can take the Delbar complex on C3 minus the origin and split the Delbar operator into two pieces. A radial de Rham operator and something called the tangential Cauchy-Riemann complex of S5. So the BCOV theory, the B model, has an action which looks like this. There is integral over C3 minus the origin of beta del inverse del bar beta. When you do the splitting, now you have what looks like a one-dimensional quantum mechanics, momentum PQ dot. I don't know if you've ever seen quantum mechanics, but the action is PQ dot, P the Q over the T. So here I'm getting a quantum mechanics based on a symplectic pairing, which is literally the symplectic pairing we had before, beta del inverse beta, the beta. And then there is this tangential complex, which is like an extra differential, so I get a derived phase space. And the interactions too, I wrote only the quadratic part of the action, there is a cubic part. All of these interactions in principle will give you a dg phase space, and the conjecture will be that this is isomorphic to the one I got from the quiver. This conjecture is just a restatement of the previous conjecture. This is not an extra. The extra thing would be if you can go beyond, beyond the classical limit and really show that if you quantize the BCOV theorem C3 minus the origin, you get the same as this quantum mechanical system with its cube. I don't know how to go to prove it because defining the quantum BCOV theory is tricky. It's mathematically rigorous. Costello-Lee defined quantum BCOV on C3. And I think the definition, the quantization has to do with local counterterms. It shouldn't matter if you're on C3 or C3 minus the origin. But a very important point of the paper is that the quantization of this B model is ambiguous unless you impose that D-branes exist and can be coupled in a specific way. So before I continue this discussion, I want to move to the situation with open strings and D-branes. So that will be the next step, to add D-branes to the matrix model.
Yeah,
any questions?
Of course, I do not understand a single word on this slide, but so BCOV well, this Q is essentially just differential operator, or if you like, a simple case, odd vector field with bracket to itself equal to 0. Q square
Yes,
equal to 0.
that's right.
All right. What BCOV
So
adds
BCOV
to this structure?
BCOV is a theory defined on three-dimensional complex Calabi-Yau manifolds. So it's not a one-dimensional, it's a three-dimensional theory. On the other hand, when I look at a Q like the one in this slide, I see, as I said, it's the quantization of something made out of position and momentum. It's a BRST operator in a quantum mechanics, essentially.
Mm-hmm.
So this looks like a one-dimensional topological system. So how do I match a one-dimensional topological system with something which works on a Calabi-Yau manifold? And an idea is to do a Kaluza-Klein reduction. You take this six-dimensional manifold, which is three-dimensional complex, and reduce on the angular directions to get just a radial evolution. And the conjecture is that this radial evolution classically matches Q. But as I said, it's not an extra statement. It's just a literal restatement of this previous conjecture, because
yes, so which means that categorically or whatever algebraically BCOV it's the same as BV structure on something, or it's more.
Yeah, well, BCOV has to do with polyvector fields, divergence-free polyvector fields. So there is an action, and the equation of motion is that the polyvector field is divergence-free. Sorry, the polyvector field is holomorphic.
Yeah, but then you quantize this story.
Yes, that's right. There's a quantization, which is done in C3, which is a very interesting story, very interesting paper by Costello-Lee, which I think has a lot of implications. But so I would like to, in principle, I would like to show that this quantum BCOV, if I do this Kaluza-Klein reduction, becomes the quantum mechanics that I'm talking about.
Okay.
And this quantization is challenging. They have infinitely many counter terms that have to be fixed.
But it's indeed some physics theory. It's nothing to do with categories and more abstract stuff.
I would disagree. I'll show you the categories in a moment.
So this BCOV is the thing that
okay.
should. So can I ask a question? So the BCOV
Yes.
is the thing that should be mirrored to higher genus invariance in symplectic geometry, or is this a different?
Yes, it's on the B model side. So
Yeah.
BCOV indeed controls the genus expansion of the DB core.
Okay.
This field beta lives in the cyclic homology of DB core.
Something
basically.
indeed which I do not. So DB core doesn't have kind of these extra structures without mirror symmetry. There is no genus expansion or whatever, and you want to add it.
It does have a genus.
I mean, formally it does, but what mathematically, if you have DB Koch, how you see this genus expansion?
Yeah, so the point is that the B model, although it's a string theory, it can be treated as a quantum field theory. So what Costello and Lee do is, instead of trying to do the genus expansion, they just treat it as if it was a quantum field theory in C3. This you cannot do on the A side because the A side is very non-local. But the B side is very local, and somehow you can bypass the genus expansion completely. I will elaborate.
All right.
Good. First, I want to add D-branes. Or let's go back to the matrix model. I want to insert a determinant inside the matrix model. So determinant, you take determinants are determinants of matrices. So to build a matrix, I'm going to take a linear combination of words and take the determinant of that. So I get a bunch of new couplings, these S's. A useful way to treat the determinant is to think about it as a Grassmann integral. So you add extra degrees of freedom, which are fundamentals, like n by 1, psi, and psi dagger. And then you write this Grassmann integral. You can generalize this by taking n by k auxiliary variables. You get something called the k determinant, at least by me, which is a generalization of the product of k determinants. Essentially, you promote the S's to matrices. So you have this deformation, this modification. It's not a deformation, it's a modification of the original integral, which now depends on the G's and on k by k matrices of couplings S. You see these couplings parameterize linear combination of words. So S's are pretty much an element, are going to be an element of the Kusul dual algebra, are going to be an element of the Ginsburg algebra. Okay. Now, in the BV formalism, you need to add some anti-fields for the fermions. That's not a big deal. What happens is the couplings get promoted to k/k matrices, because now you have fermions and anti-fermions, which are cos number 0 and 1, and different Grassmann parity. So let me call these extended couplings sigmas. They're analogous to the taus before. They are just the most general deformation of this BV action by mesons. And they live in, as I said, they're matrix valued elements. Sorry, they are matrices valued in a Schrick. So matrices valued in the Ginsburg algebra. Any questions? Okay. So now you repeat the story. We look at delta BV acting on this new action, which includes both the main and the single traces. And I look for differential operators that compensate the action of delta BV. One is what we already, so the Q that we had before is now called Q closed. So that's a function of tau, it's a differential operator in tau. But now there is a new contribution, which is this Q open, which is differential operator in tau and sigma. Q closed squared to 0 by itself, the square of Q open plus Q closed acting on Q open is 0. You could call this an open-closed BV infinity algebra. I know I've seen my papers with terminology like open-closed homotopy algebra, OCA. This is an open-closed BV infinity algebra. Open is a little bit more complicated than closed. That's why I'm not even writing it down. It has like 5 or 6 terms. Some of the terms that just give you the differential and composition of a Schrick. And then there are many others. There is a nice map from these to the cyclic homology and more. But as I said, this is some second-order differential operator made out of these sigmas and taus.
Yeah, but I'm confused. The space on which this new whatever dg vector field acts, previously it will be a sum, was a sum of a cyclic.
So let's not confuse the quantum and the classical. In the quantum case, it was just the cyclic homology. It was just tau. So it's a differential operator in tau. Now now I have a differential operator, so the V infinity algebra structure, on the combination of a commutative and a non-commutative formal pointed space. There's a commutative formal pointed space with coordinates tau, and a non-commutative formal pointed space with coordinates sigma. And there is a differential operator that acts on the product of these two, and it has this vibration structure. See, there is a piece of the differential just has to do with taus, and the other mixes taus and sigmas.
So I forgot, what are non-commutative taus or sigmas?
The sigmas. See, the sigmas were the
non-commutative and taus commutative, yeah?
Yes. Taus are the ones from the previous slides, sigmas are new.
Okay, and so the space on which this combined, whatever complicated Q lives, it's a product of these two dg manifold, well, graded manifolds with some projection structure, whatever.
Yes.
Relation structure. Okay.
Yes. Now we can take the classical limit. So we replace derivatives with pi's and sort of rows, if you want. So now we have a space which has tau and a symplectic manifold now, which has coordinates tau and pi and sigma and rho. Sigma and rho are sort of, so this classical limit has 2 pieces. The sigmas and rho give you a double of the Ginzburg algebra. So you get a 2D cyclic Calabi-Yau structure which is double of the Ginzburg algebra, and which is fibered over the phase space that we encountered before.
So may I ask you a stupid question, because it's about matrix integrals. Basically, you model branes in the metric model, yeah, boundary conditions. How do I see it? I mean, you consider some modifications which probably is supposed to, yeah. Why? How?
Remember that the Riemann surfaces come out from these ribbon diagrams, right?
Yeah.
Where these are the x's propagating.
Yeah.
Now I added some psi's with couplings to the x's. These psi's have a single index, right? But if you want, they are K-by matrices. There are 2 types of indices. There is the index of the gauge index and the flavor index. And the flavor index sort of doesn't do anything interesting. It just closes into a loop. So the result is a surface with boundaries.
Okay.
The boundaries correspond to the flavor loops. Yeah.
Right. Funny.
That's why you get D-branes. Right. So it's important that things sort of are bilinear in these fundamentals. And when you integrate away the fundamentals, you get these determinants. Okay. So again, I can try to find this extra structure in Calabi-Yau cones. The idea is to look at something called holomorphic Chern-Simons theory on the cone. concretely, it just means that I'm looking now at forms on the cone minus the origin. Forms with the pairing. And my conjecture is that forms with this pairing are quasi-isomorphic to this double of the Ginzburg algebra. I mean, the Ginzburg algebra kind of gives you, holomorphic functions on the Calabi-Yau, right? And I'm saying, well, the double adds some 0,2 forms, like the Beltrami-Martinelli kernel again, dual to those. So this slide is a little bit shorter than perhaps it should have been. But anyway, so I'm just saying there is this forms with this pairing. It's a nice symplectic manifold. You can make a non-commutative version by taking matrices of forms. And then these matrices of forms talk naturally to polyvector fields. Polyvector fields deform the Calabi-Yau cone, and the forms are fibered over this deformation space.
Sorry, when you say holomorphic Chern-Simons theory, is it classical or
Classical, and then we can quantize.
Maybe you can quantize. I can't.
Well, not me. Costello Lee can
quantize. Yeah, but
yeah. So it was an integral of omega wedge, like A delta A. Plus A cubed.
So, but when you say this, ask a question that something is quasi-isomorphic to the double of Ginzburg algebra.
So the double is defined specifically by an equation, which is not written by this, by the classical limit of this.
Yeah, but you do not need to take whatever you holomorphic Chern-Simons theory to take.
No, absolutely. So this is homological algebra state.
Yeah, it's homological algebra. But then, what is quasi-isomorphic to this D gamma? It's quasi-isomorphic.
It's isomorphic to forms. See, omega also 3 minus the origin.
All right. So there is no this Hooft large n expansion.
Nothing.
There is nothing
no,
like that.
Absolutely.
All right.
Yep. And so again, this is also a theorem I would love to see proven. This double of the Ginzburg algebra is really weird. I mean, because it's not it's an infinity algebra. It really has higher operations baked in.
Yeah, I would like to understand more about it. And actually, we should decide, because I see that you have 8 more or whatever.
I'm ready for the next lecture too. I mean, I'm happy to stop at any point.
Yeah. So then you should decide where it's convenient to make kind of.
I think I would like to show the next slide and then I can stop.
Yeah. Okay. Yeah. Show it. Yeah.
Okay. So here there is the classical statement, which is already interesting to ask. It would be nice to prove it for a generic Q and W.
Some double of Ginzburg algebra is quasi-isomorphic to polyvector fields.
No, to forms.
Excuse me, to forms on this with this pairing. Yeah, it's actually okay.
And then, if you're more ambitious, we can start talking about quantization. Now, what Costello and Lee showed is that if you take BCOV and homomorphic Chern-Simons, so if you take the tau, the forms and the polyvector fields together, and you require the quantization to have a certain structure, where the polyvector fields talk to the forms in a specific way, which is governed by string theory, then the quantization is unique. It's a very big paper. I mean, I've been trying to understand that paper for years. So that motivated the whole thing.
I have not started yet. Yeah, all right. So
because it says that closed strings are hard to quantize, open strings are hard to quantize, but if you put them together, the quantization is unique and it exists.
But
Much
when you say quantization, you mean some physics procedure. You mentioned like
It's
counter terms.
Costello-Lee. It's the math procedure. It's not a physics procedure. It's a
No, no,
math
no. I mean
procedure.
that what mathematically, all right. So that
So
I
it
don't
means
want to
it means
start this discussion, but
that
mathematically, you should start with some mathematical object and continue
yeah,
with mathematical
you're
counter
trying to define a
terms.
factorization algebra on
Okay,
homomorphic factorization algebra on C3
on C3.
over formal power series in H bar.
Okay, that's good. But in order to define this factorization algebra,
There
should
are
I?
abstractions.
Hmm?
There is an abstraction complex.
No, no,
Uh,
but to start with, I have what classical holomorphic
Classical
Chern-Simon
factorization algebra.
section, and yeah, okay, all right.
And you can
Mhm.
so there's a quantization in terms of Faman diagrams, which is explicit, but has abstractions because you need to find some counter terms. And there is an abstraction complex, which is you can just write down. And this abstraction complex mixes the two. And somehow what saves the day is that every term every counter term in the Chern-Simons action can be absorbed into a shift of the closed string fields. So it's really important that the closed strings are the cyclic homology of the open strings. And conversely, the counterterms to the closed strings are very constrained by the fact that they need to couple to the open strings. So together, these two things give you a completely trivial deformation complex. Somehow, he has he shows that the deformation complex of 1/2 is like cyclic homology, the other is negative cyclic homology, and there is a connecting map to periodic cyclic homology, which then vanishes.
I see. So he start with classical factorization algebra, write down the deformation complex, yeah,
Yeah.
and then he wants mm, to construct a very concrete deformation which should correspond to the quantization of the Chern-Simons. So, and for that there are abstractions and somehow what you spelled out in physics terms like counter terms, blah blah blah. So they kind of show that the abstraction vanishes
Yes.
mathematically.
I think it would be very nice to express it in the language of open-closed homotopy algebras, which is
Yeah.
why mathematicians talk about these open and closed situations. Something where you have sort of a closed deformation problem and an associated open deformation problem. And somehow the deformation complex of this open closed algebra vanishes, even though the individual deformation complexes are interesting.
Yes. So.
And in a sense, the very abstract perspective that was behind this calculation is what makes me hopeful that the quantization can be done, because I feel that perhaps once you match the classical problems, perhaps the deformation complexes will both be unabstracted and unique somehow, and then you know that you quantize one, you quantize the other, you must get the same answer just because it's unique. That would be my hope. Maybe it's optimistic.
Yeah.
But I feel that in string theory there is a vague chance that matching things classically is enough.
Yeah. All right. So maybe.
Yeah, this is also what I was saying in words. Sorry, I forgot to.
Yeah. Maybe I don't know. Maybe it's good time to stop. Yeah,
Yes.
and also maybe it will give time people to look at least in the Castello-Lee. It's Castello-Lee. Is it the only paper or there is a title?
Yeah, it's one paper. It's quantization of open close.
Yeah.
BCOV.
And it's done in the language of factorization algebras, which is different from the language of A-infinity categories, which people get used to in homological mirror symmetry. Yeah.
But somehow classical open strings are always secretly about the infinity algebras.
Yeah,
So
that's
when you
true.
need to make a translation, somehow it's not a factorization algebra where you match to categories and stuff. It's open-close factorization algebra. So open-close factorization algebra somehow have a structure such that the open strings contain an infinity category.
Yes.
So
Okay.
somehow, holomorphic
Yeah,
summons is literally about complexes of space-filling branes.
Yeah.
dg-core.
Yeah.
Classical solutions of Chern-Simons are literally dg-core.
Yes, of course, because critical points of holomorphic Chern-Simons are holomorphic vector bundles.
Absolutely.
Yeah, and zeros of this thing should be objects of the category. Okay, so great and very still mysterious for me. Are there any questions? Well, if not, then tomorrow David gives his third and last lecture.
We move to chiral gauge D-branes.
Yeah, it's local time is 3:30 and in Toronto it's 4:30.
Yes.
So it's all right. Thank you very much.
Bye.
Thank you. Bye.